In this session, we are going to talk about 11th Physics, chapter number 4, Laws of Motion, part 6. First point is collision in two dimensions, that is an head-on collision. In this case, the direction of at least one initial velocity is not along the line of impact. In order to discuss such collisions, mathematically it is convenient to use two mutually perpendicular directions as shown in figure 4.4. One of them is the common tangent at the point of impact, along which there is no force, or along this direction there is no change in momentum. The other direction is perpendicular to this common tangent through the point of impact in the two-dimensional plane of initial and final velocities. This is called the line of impact. Internal mutual forces exerted during impact, which are responsible for change in the momenta, are acting along this line. From figure 4.4, u1 and u2 initial velocities make angles alpha 1 and alpha 2 respectively with the line of impact, while v1 and v2 final velocities make angles beta 1 and beta 2 respectively with the line of impact. Let us consider figure for oblique or non-head-on collision, which is as shown in figure 4.4, where all symbols have as usual their meanings. From figure and respective consideration, we can assume that according to conservation of momentum along the line of impact, m1 u1 cos alpha 1 plus m2 u2 cos alpha 2 is equal to m1 v1 cos of beta 1 plus m2 v2 cos beta 2 as equation 4.12. As there is no force along the common tangent, then m1 u1 sin alpha 1 is equal to m1 v1 sin beta 1 as equation 4.13. m2 u2 sin alpha 2 is equal to m2 v2 sin beta 2 as equation 4.14. Therefore, E is equal to minus v2 cos beta 2 minus v1 cos beta 1 whole divided by u2 cos alpha 2 minus u1 cos alpha 1. Therefore, E is equal to v2 cos beta 2 minus v1 cos beta 1 whole divided by u1 cos alpha 1 minus u2 cos alpha 2 as equation 4.15. Equations 4.12, 4.13, 4.14 and 4.15 are to be solved for four unknowns v1, v2, beta 1 and beta 2. Now, next point is impulse of force, which can be explained in animation as
impulse of a force. In case of a ball hit by a bat or driving a nail into the wooden block with a hammer, the force acts for a short time interval. This force varies with time, hence cannot be measured easily. In such cases, we measure the total effect of the force called as impulse of force. Consider an impulsive force vector F acting on a body of mass m for short time t. The velocity of the body changes from vector u to vector v. According to Newton's second law, vector F is equal to vector p2 minus vector p1 upon t. Impulse of the force or impulse vector F dot t is equal to vector p2 minus vector p1 that equals to vector j that equals to m vector v minus m vector u. This shows that impulse is equal to the change in linear momentum of the body. Impulse is a vector quantity. Its direction is same as that of the force. The SI unit of impulse is same as that of linear momentum, that is kg meters per second or Newton seconds. Dimensions of the impulse are L raised to 1, m raised to 1, t raised to minus 1.
Impulse of force explained as according to Newton's first laws of motion, any unbalanced force change linear momentum of the system. That is, basic effect of an unbalanced force is to change the momentum. According to Newton's second law of motion, vector F is equal to vector dp upon vector dt. Vector dp is equal to vector F into dt. The quantity change in momentum is separately named as impulse of the force vector j. If the force is constant and is acting for a finite and measurable time, we can write the change in momentum in time vector j is equal to vector dp, which is equal to vector p2 minus vector p1 is equal to vector f dot dt as equation 4.16. For a given body of mass m, it becomes vector j is equal to m in bracket vector v2 minus vector v1, which is equal to vector f dot vector dt as equation 4.17. If f is not constant but we know how it varies with time, then vector j is equal to delta vector p integration vector dp is equal to integration vector f dt as equation 4.18. First, colliding objects experiences force along the line of impact which changes the momenta. For their system, these forces are internal forces. These forces form an action-reaction pair which are equal and opposite and act on different objects. Second, there is no force along the common tangent that is perpendicular to the line of impact. Third, in reality, the impact is followed by emission of sound and heat and occasionally light. Thus, in general, part of mechanical energy, kinetic energy is lost, that is converted into some another non-recoverable forms. However, total energy of the system is conserved. 4. In reality, velocity of separation, that is relative velocity, that is final, is less than velocity of approach, relative initial velocity along the line of impact. Thus, coefficient of restitution is less than 1.5. Only during elastic collisions, atomic and molecular level only, never possible in real life. The kinetic energy is conserved and the velocity of separation is equal to the velocity of approach, or the initial relative velocity is equal to the final relative velocity. Thank you.